We're now going to move on to a fairly familiar topic, one that many of us have seen many times before back in high school or possibly even earlier. And that's the idea of congruence of triangles. Now, intuitively, we're going to say that two triangles are congruent if they basically would lie right on top of one another. If you could move them around without stretching them or squashing them or twisting them, and lay one right on top of the other and have it exactly match up. This is the intuitive notion of congruence, and it can be made precise using the theory of rigid motion and talking about how we move things through space without changing their internal structure. However, we're going to need a slightly different approach. It's difficult to make the idea of rigid motion really precise, and so we're going to take an approach where we just look at two triangles. We say we're going to associate this vertex on the first triangle with this vertex on the second triangle, so forth and so on. That's going to give a correspondence of the sides of the triangle and the angles of the triangle. And once we have all that, then we'll be able to say that the two triangles are congruent if all of the component pieces of the triangle are congruent. So, let's start with the following notion: a correspondence between a triangle ABC and a triangle DEF is a bijection between their vertices. For example, we could take the bijection A goes to D, B goes to E, and C goes to F. This is a bijection between the set of vertices of the first triangle and the set of vertices of the second. And we can write this in a more compact form, because we'll want to talk about this reasonably often, as ABC corresponds to DEF. And what this means is that the first item in the list on the left corresponds with the first item on the right. The second item on the left corresponds with the second item on the right. And the third item on the left corresponds with the third item on the right. It's just a shorthand for the correspondence that we did above. Note that the order very, very much matters here. That the correspondence, let's take the correspondence ABC corresponds to EFD, is a different correspondence. Because this correspondence associates A to E, B to F, and C to D. So we want to start with the idea of a correspondence between triangles. Now, any correspondence induces correspondences of edges and angles. So, for instance, in the initial correspondence we had, ABC goes to DEF, we would also have that the segment AB corresponds to the segment DE. And the way that we come up with this correspondence is we simply replace each point in the segment on the left with its corresponding point in the segment on the right. A corresponds to D, and B corresponds to E, so the segment AB corresponds to the segment DE, and we'll often talk about pairs of corresponding sides given a particular correspondence. So similarly, we have that the segment AC corresponds to the segment DF, the segment BC corresponds to the segment EF, and for angles, we have that the angle BAC corresponds to the angle, and once again, we just replace each point with its corresponding point. So B corresponds to E, A corresponds to D, C corresponds to F, angle ABC corresponds to the angle DEF, and the angle ACB corresponds to the angle DFE. So a correspondence between triangles induces 6 separate correspondences, 3 between sides and 3 between angles. And when all of those correspondences are between 2 things that are congruent, either 2 segments that are congruent or 2 angles that are congruent, we're going to say that the correspondence between triangle ABC and triangle DEF is a congruence. So, definition 44, given triangle ABC, triangle DEF, and correspondence ABC to DEF, if each pair of corresponding sides and angles are congruent, we say the correspondence ABC to DEF is a congruence, and we write that triangle ABC is congruent to triangle DEF. Now, we need to be careful here. When we write that 2 triangles are congruent, the order that we describe the triangle in matters. So, for instance, if we say that the triangle ABC is congruent to the triangle DEF, this means, among other things, that the segment AC is congruent to the segment AF, for example, because A and C are in the first and third positions on the left, and D and F are in the first and third positions on the right. So even though a triangle can be written in multiple different ways, triangle ABC and triangle BAC are the same triangle, when we go to write down the congruence between triangles, we need to make sure that we have the order correct, because the order can matter. Now, you may remember that we have various theorems regarding congruence. Congruence on its own says that we've got 6 separate congruences. 3 segments are all congruent to one another, and 3 angles are all congruent to one another. But the fact is that we don't actually need all 6 of those. We don't need to prove all 6 of those in order to know that a triangle is congruent. We're familiar with various theorems that tell us that if we have, say, 3 of these correspondences being congruences, then that means that the triangles themselves are congruent. However, it turns out that we can't actually prove any of those just based on what we have. That none of the familiar triangle congruence theorems can be deduced simply from what we've had so far. Thus, in order to talk about congruence of triangles and get some theorems in here, we are required to introduce a new axiom. And the axiom is going to be one of the congruence theorems. One of the theorems that says that if we have a certain collection of sides congruent and angles congruent, then the triangles themselves are going to be congruent. Now, in theory, we could take quite a few. We've got a few options for what we could take, but we are going to follow the most traditional method here and use side angle side as our axiom. So axiom, we're going to call it side angle side, or the side angle side postulate. It says that if triangle ABC and triangle DEF are triangles, the segment AB is congruent to the segment DE, the segment AC is congruent to the segment DF, and the angle at A is congruent to the angle at D, then triangle ABC is congruent to triangle DEF. So let's look at what this is saying with an example. Let's suppose that we've got two triangles. And let me go ahead and mark them. Let's suppose that we've got A, B, C, D, E, F. We've got these two triangles, and let's see what we know. We know that the segment AB is congruent to the segment DE, so we can mark those two segments as congruent to one another. The segment AC is congruent to the segment DF, and then the angle at A is congruent to the angle at D. And what this axiom says is that if we have these three congruences, then the other congruences are all going to follow as well. If we have both of these, then in particular that means that the segment BC will be congruent to the segment EF, that the angle at B will be congruent to the angle at C, and the angle at E, rather, and that the angle at C will be congruent to the angle at F. So we have to take side angle side as an axiom. But once we do that, then we get this theorem that we can, or not this theorem, but the statement that we can use, and use it to show all of the other theorems that we have relating to congruence of triangles. So let's look at some applications of side angle side, including some ones that we're going to use very, very often throughout the rest of the course. So let's look at theorem 45, which is the Isosceles Triangle theorem. It says, if two sides of a triangle are congruent, then the angles opposite them are congruent. So, isosceles triangles are one of the types that we tend to be most familiar with. Let's take an isosceles triangle here. And while we're not going to use this picture in the proof, we are going to use it to try to organize our thoughts. So let's think about how we might prove this. So we've got this triangle here, and what we're told is that two of the sides are congruent to one another. And what we're supposed to try and prove is that the angles opposite them are congruent. So angles opposite congruent sides are congruent. So we're going to prove this via an application of side angle side. Now, at first it seems like we don't have enough to use side angle side because we only have one triangle. But in fact, we can look at correspondences between a triangle and itself, and side angle side still applies there. Nothing in side angle side required that the triangles that we looked at be distinct triangles. So let's consider the correspondence ABC to ACB. So we're looking at the same triangle, but we're sort of just writing it in a different order. We're considering the vertices in a different order. One ABC and one ACB. So, by our to start this off, we really should say, let triangle ABC be a triangle with the segment AB congruent to the segment AC. We really should put in the language to correspond to the figure that we've drawn. So now let's consider the correspondence ABC goes to ACB. So we have that the segment AB is congruent to the segment AC. That was part of what was given here. So that gives us that the segment with vertices at A and C corresponds to the segment with vertices at A and B. And we have that AB, the segment AB, is congruent to the segment AC. So this is looking at AB here and AC here. And so that's, of course, just saying the same thing but switching the order because congruence is symmetric. And then also we have that the angle BAC is the angle on the left side of this congruence is congruent to the angle CAB, the angle on the right side of this congruence, because they're the same angle. Therefore, by side angle side, we have that triangle ABC is congruent to triangle ACB. Now this means many things. There are 6 different correspondences here. To say that 2 triangles are congruent means that you have 6 different congruences you can talk about. But we're particularly interested in the congruence of angles. So that means that the angle ABC, coming from the left, is congruent to the angle ACB. And that finishes the proof, because that shows that the 2 angles that we're looking at in the problem are congruent to each other. So as I said, we're going to use the Isosceles Triangle theorem a lot. Many of the constructions that we're going to do are going to involve triangles that have 2 sides being the same length, and therefore the opposite angles are going to have the same measure. That is, they're going to be congruent to one another. Corollary 46 states that all equilateral triangles are equiangular. So equilateral means all sides congruent. Equiangular means all angles congruent. And this one's not too hard to see. We won't even write down the proof of this. We'll just talk it through. If I have an equilateral triangle, well then, if I look at the side AB and the side AC, those two sides are congruent, and therefore the angles opposite them are congruent. But if I look at the side AB and then the side BC, those two sides are congruent also, and so the angles opposite them have to be congruent, which means that the angle at A has to be the same as the angle at C, and so that shows that all three of the angles are congruent to one another. So not too hard to see there. So using side angle side, we can prove the other congruence theorems that we work with. And there are quite a few of them to look at. Let's start with angle side angle. So this is going to be theorem 47, which is angle side angle. It says, given triangle ABC and triangle DEF, if we have that angle A is congruent to angle D, angle B is congruent to angle E, and the segment that lies between those two angles is congruent to the corresponding segment that lies between the two angles on the other triangle, then triangle ABC is congruent to triangle DEF. So, picture here is, picture here is that if we've got a pair of angles, or two pairs of angles that are congruent, and then the side between them is also congruent, then that means that the whole triangle is congruent, that we have the other three congruences between the triangles. So let's see how we might do this. Now, one of the ways that we are usually going to prove these sorts of theorems is to take one of our figures and copy it onto another one. So, in particular, let's go ahead and do that here. Let's call this A, B, C, D, E, and F. And so let's suppose that we have this situation, and we want to prove that the triangle on the left, ABC, is congruent to the triangle on the right, DEF. This is almost always going to come down to using one of our previous congruence axioms or theorems. At this point, we only have the one congruence axiom, side angle side, and so what we would like to prove is that another one of the sides in the triangles are congruent. We'd like to prove that, for instance, the segment AC is congruent to the segment DF. That would work because then we would have a pair of sides with the angle between them congruent, which would be enough to use side angle side. So what we're going to do is the following. We're going to basically see, well, what happens if the segment AC is not congruent to the segment DF? So let's let C prime be in the ray DF such that segment AC is congruent to segment DF. We know this is always possible by the segment construction theorem, although we will often not specify that. Now, what we're going to what we want to show is that this C prime actually has to equal F. But let's see why that has to be. So the way to see why that has to be is to try constructing a situation where it isn't and see what goes wrong. So what would happen if the point C prime, such that made AC congruent to DC prime, sorry, I just saw something that made this whole thing confusing. I want to choose C prime and DF such that segment AC is congruent to the segment DC prime. We're trying to prove that segment AC is congruent to segment DF, but we don't know that yet. Sorry about that. What we do know now, though, is that the segment AC is congruent to the segment DC prime. So that means that by side angle side, we have that triangle ABC is congruent to triangle DEC prime. Because the green angles are congruent, the red sides are congruent, and the yellow marked sides are congruent. Therefore, the triangle ABC is congruent to the triangle DEC prime, wherever C prime happens to be on this ray. Now, therefore, this means that the angle DEC prime is congruent to the angle ABC. So that means that the angle DEC prime has to be congruent to the angle ABC, but angle ABC is also congruent to the angle DEF, and now we start to see where we're going to be able to find our contradiction. So, or not contradiction, but get to our conclusion. Because notice that right here we have both the white segment and the yellow segment coming off of E are both forming an angle with the red segment that is congruent to the angle ABC. Now, we are almost done because the angle construction theorem says that there's only one angle. There's only one ray that forms a given angle at a point with another ray on the same side of that line. So notice that since C prime is in the ray DF and is not in D, C prime is on the same side of the line DE as F. This was by Theorem 24. So, by the angle construction theorem, there is only one ray, I'll say EG, with G on the F side of the line DE, such that the angle DEG is congruent to the angle ABC. So there's only one ray that comes off of E that makes the blue angle with the ray ED. That means that since the ray EF forms that angle and the ray EC prime forms that angle with the ray ED, so they have to be equal. And this is since the angle DEF is congruent to the angle ABC, which is congruent to the angle DEC prime. So the ray EF and the ray EC prime have to be the same. So that means that C prime has to belong to the line EF, but by construction, we also know that it lies on the ray DF, so it lies on the line DF, but these two lines, EF and DF, only intersect in one point F. So that means that C prime equals F. So we already showed up above that triangle ABC is congruent to triangle DEC prime, and we've just shown that C prime is actually equal to F. So we're done. So we showed that we have the angle side angle congruence theorem for triangles, that if you have two angles congruent and the sides between them congruent, or two pairs of angles congruent, I should say, and the side between them congruent, then you have a pair of congruent triangles. You have all the other congruences involved. Angle side angle allows us to get a sort of converse to the isosceles triangle theorem. Corollary 48 says that if two angles in a triangle are congruent, so are the opposite sides. So this is going to follow a very similar argument to what we had before for the isosceles triangle theorem. If we know that these two angles are congruent, we want to show that the sides opposite them are congruent. So the proof goes similarly. So let's suppose that the angle at A is congruent to the angle at C. So that means that since the segment AC is congruent to the segment CA, we have that the triangle ABC is congruent to the triangle CBA by angle side angle, because we have the angles at A congruent, or the angles in first and third positions are congruent to each other, and the segment that that connects them is congruent. So therefore, the segment AB is congruent to the segment BC, because we have this congruence of triangles. And then a similar corollary to this one, which says that every equiangular triangle is equilateral. So if we're looking at triangles, if they're equilateral, all the same sides, then their interior angle measures are all the same, and vice versa. So we will use the isosceles triangle theorem very often. We'll use this corollary that sort of goes the other way, the converse to the isosceles triangle theorem, slightly less often, but we will definitely use it. Okay, so the next congruence theorem we have is side, 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 which says that if I've got two triangles and I know that all of the corresponding pairs of sides are congruent, then we have a congruence of the triangles themselves. That is, all the pairs of angles are congruent. This is actually going to take significantly more work than the proof of angle side angle. And that's because at the beginning we have no information about angles. When we were working with angle side angle, then we knew something about the sides and we knew something about the angles. We had information about both kinds of objects we're looking at. For side, 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 we don't have that. We only have information about the side lengths, and it turns out that that's going to make things a little bit complicated. So let's go ahead and see what we can do about this. So theorem 50, side, 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 says that if, or let me write it this way, given triangle ABC and triangle DEF, if AB is congruent to DE, AC is congruent to DF, and BC is congruent to EF, then triangle ABC is congruent to triangle DEF. All right, let's see what we're going to do here. Now, before starting the proof, we want to come up with a strategy, or at least get some idea of how we might approach this. Now, I'm going to draw some sort of random triangles here, although, as we'll see in a second, we've got to be a little bit careful that we don't let the specifics of our drawing influence us too much in the process. All right, so let me give them some labels: A, B, C, D, E, F. All right, we know AB is congruent to DE. We know AC is congruent to DF, and we know BC is congruent to EF, all those segments. And that's what we know. And we want to try to conclude that these two triangles are congruent to each other. The only real good ways we have of doing that are using either side angle side or angle side angle. And the difficulty, as I mentioned, is that we don't have any of the angles. We don't have any angles here. So what we're going to do is we're going to copy the triangle DEF over onto the figure of triangle ABC. But what we're going to do is we're going to do it below there. And we're going to do this in a particular way. We're going to construct this point here, and the way that we're going to do it is the following. We can make sure by angle construction that we construct a ray that forms an angle like this, the green angle. Furthermore, we can make sure that that segment has the right length, that it has the length DE. And that'll give us another point down here, which I'm going to denote B prime. And then we'll have some sort of triangle like this, triangle AB prime C. But now what you'll notice about AB prime C is that it's going to be congruent to the triangle DEF. It's going to be congruent to triangle DEF by side angle side, because the red sides are the same, the blue sides are the same, and the green angle in between them are all the same. So we're going to be able to get this right here. And that's where things are really going to kick off. Once we're here, we're going to be able to start drawing in some new triangles using the Isosceles Triangle theorem to do some work. So let me try to move these figures over here, just so that we don't use up too much space that we could use for writing out the proof. So by the angle segment construction theorem, there is a unique point B prime on the opposite side of the line AC from B, such that the angle CAB prime is congruent to the angle FDE, and I realize that I just lost my F point over here, is congruent to the angle FDE, and where the segment AB prime is congruent to the segment DE. Now, by side angle side, the triangle AB prime C is congruent to the triangle DEF. What we're going to do now basically is prove that the triangle ABC is congruent to the triangle AB prime C, which, as it turns out, will be enough to prove congruence of the two triangles. Congruence of triangles is, in fact, an equivalence relation, as all of our congruences are, and so that will be good enough. So we wish to prove that triangle ABC is congruent to triangle AB prime C. All right, so now that we've got that in hand, let's attack this problem. Before we go to a new page, I want to, no, let me do this on the next page. I'm going to take our diagram here. So here's where we're at. And one thing that we can use is the following. We know that B and B prime are on opposite sides of the line AC. That's how we constructed it. Now, what that means is that if we draw the segment between them, that has to intersect the line AC at some point G. So, continuing on the proof, since B and B prime are on opposite sides of the line AC, there exists G such that G lies between B and B prime, and G is on the line AC. Now here's where some of the extra work is going to come in, because we've sketched out this problem in such a way that makes G lie on the segment AC. It lies between A and C. But that doesn't have to happen. We could have other situations. G could actually lie anywhere on the line AC, and we have to consider all the possibilities. We'll handle this one first, and then we'll see some of the others. We are going to be able to combine a couple of the cases that we have to work with. So let's look at the situation that we actually have sketched out here. And now we want to look at some of the other triangles involved. So notice that, so let's suppose, sorry, before we do that, we need to suppose that, sorry, I want to be even more explicit about this. So we consider several cases. We need to consider all the cases, but we're going to break the problem up into several cases. So case 1, let's suppose that G actually lies between A and C, the situation we have here. Now, what we would really like is to be able to use either side angle side or angle side angle, which means that we need some way of getting at the angles involved in the problem. The Isosceles Triangle theorem is exactly how we're going to do it. Now, that means that we need to find some triangles that are isosceles, which means that we need to use a triangle with the red sides, the red segments as sides, and the green segments as sides, because those are the ones that we know are congruent to one another. So, the triangle ABB prime is isosceles. So that means that the angle ABB prime is congruent to the angle AB prime B by the Isosceles Triangle theorem. So that gives us an angle, let me use yellow, ABB prime is congruent to AB prime B. We can do, of course, the same thing on the other side. Similarly, the triangle CBB prime is isosceles. So that means that the angles opposite the two congruent sides are congruent. So that means that the angle CBB prime is congruent to the angle CB prime B. So there we go. Well, now we would like to conclude that the angles ABC and AB prime C are congruent. We do need to be careful, though. In particular, we are very much working under the assumption that G lies between A and C, so we better make sure that shows up somewhere. Or, you know, maybe our argument works for every case, but it doesn't. We need to be very careful here. We have, since G is an interior point of the segment AC, it is in the interior of angle ABC. And in the interior of angle AB prime C. Therefore, by the angle addition theorem, that tells us that angle ABC is congruent to angle AB'(C). So the angle addition theorem requires us to make sure that the two angles that we're looking at really do lie inside a single big angle, which means that the ray, which where the two angles that we're adding together basically are adjacent to one another, that ray has to lie in the interior of the big angle that we're trying to work with. And so in order for this theorem to work, we needed to know that G here lay in the interior of angle ABC so that we could conclude that, actually we want the blue angle up here and the blue angle down here are congruent in order to use angle addition. Pardon me. Now that we've got that the blue angles are congruent, then we're done. Now we can use side angle side. So by side angle side, this tells us that the triangle ABC is congruent to the triangle AB'(C), which is what we wanted to prove. All right, so that was one of the cases. Let's consider another one of the cases. So when the point G lies on the line AC, there are actually 5 separate cases that we could have. We could have that G lies between A and C that we have here. We could have that G lies essentially to the left of A, so that A is between G and C. We could have that G lies to the right of C, so that C is between A and G. Or we could have that G is equal to A, or G is equal to C. So there are actually 5 different places that a point on a line could be relative to 2 other points. So let's consider some of those other cases. So case 2, let's suppose G equals A. So let's sketch out what this looks like and see how that helps us. So G was the point that lay directly between B and B' on the line AC. So if A and G are the same, that means we've got B and B' down here. Let's see, we've got this set up right here. And we want to show that the triangles ABC and AB'(C) are congruent. So case 2, suppose G is equal to A. So that means that so that means that the triangle B'(C) is isosceles. So that means that the angle ABC is congruent to the angle AB'(C). So we're using the whole big triangle that we've got here to conclude that that the angle here at B and the angle here at B' are congruent because they're both opposite the green sides of the triangle. But once again, that's enough because that shows us that triangle ABC is congruent to triangle AB prime C by side angle side, because the red sides are congruent, the blue angles are congruent, and then the green sides are congruent. So we have a side angle side congruence between the top and bottom triangles. All right, so what about case 3? Case 3 is similar to case 1. We're just going to use angle subtraction instead of angle addition. And once we sketch out the situation, it'll become fairly clear, and we may not go through the entire proof. All right, so let's see. Let's suppose we've got this situation. A, B, C. Here's B prime. Of course, the line AC continues on this way, and we've got the point G there. And let me go ahead and mark the congruences that we have. So, we're going to use the same sort of argument as in case 1. So we're going to look at first at triangle CBB prime. Now, triangle CBB prime is isosceles. So that means that angle CBB prime is congruent to angle CB prime B. So we'll go ahead and note them this way, because they're both they're the angles inside the big triangle that we have here. But we can also look at the triangle ABB prime. Triangle ABB prime is isosceles. So that means that angle ABB prime is congruent to angle AB prime B. So that gives us that those two angles are congruent to one another. So what we're trying to get at actually is these angles, these blue angles. And now the thing that we want to use is angle subtraction. And once again, we need to know that A now lies in the interior of angle CBG and CB prime G. So we have that since A is between G and C, A is in the interior of angle CBG, and A is in the interior of angle CB prime G. So by angle subtraction, we have that angle ABC is congruent to angle AB prime C. So that means that angle ABC is congruent to angle AB prime C by side angle side. All right, so that's 3 cases done. The good news is that cases 4 and 5 are both very similar to cases 2 and 3. So case 4, let's suppose that G equals C. So now our picture becomes the following. And now we can use basically exactly the same argument that we did for case 2. So we can say that as follows. A similar argument to case 2, just exchanging the roles of A and C, shows that triangle ABC is congruent to triangle AB prime C. So exactly the same argument goes through, except instead of looking at the isosceles triangle CBB prime, we're now looking at the isosceles triangle ABB prime and going on from there. And similarly, case 5, suppose that ACG, well, that picture looks just like the one that we just did, only the roles of A and C have been switched. A similar argument to that in case 3, exchanging A and C, shows that the triangle ABC is congruent to the triangle AB prime C. So that takes care of side, side, side. It's definitely the theorem that requires the most work, the congruence theorem for triangles that requires the most work. But it also turns out to be very, very useful in a lot of what we are going to do later on. It also is a good illustration of why we need to be careful about making sure about things like where does this point lie? We just can't assume that G lies between A and C, even though that's where we would, of course, like it to be. All right, so a few little topics to finish this off a little bit easier. Let's look at a couple of definition and a theorem involving angle bisectors. So definition 51, the ray AD is a bisector of the angle BAC if D is in the interior of angle BAC and the angle BAD is congruent to the angle DAC. So the sketch for what this looks like is fairly intuitive. We've got an angle BAC, and then we've got a ray AD that we want to claim is the angle bisector. And this requires two things. It requires that D actually lie in the interior of angle BAC, but it also requires that the two angles formed by it, that it splits off into, are congruent to one another. So this is basically the halfway point, angle-wise. Actually, this is very similar to the definition of midpoint of a segment, and one could create a fairly robust theory of duality between angles and segments, and a lot of theorems about segments have a corresponding theorem about angles, and vice versa. It would be an interesting approach, although we were not constructing quite so elaborate a framework to work in here. We don't need that. Theorem 52 says that every angle has exactly one bisector. So we'll do a sketch of this proof. As with all exactly one type statements, or there exists a unique type statements, there are two parts to it. First of all, we have to construct an example. We need to show that given an angle, there is some bisector to it. And then we need to show that, well, there's only one. So let's start off with taking an angle here, and let's try to construct a bisector for it. It turns out that actually one of the more difficult parts of this process, if you try to build things up, is showing that the thing that you construct lies in the interior of the angle. So for instance, one fairly natural approach to us would be something like, well, let's look at the angle measure of this angle. This has some angle measure r. Well, let me go ahead and construct an angle here that has an angle measure of r over 2. And this does work, but when you actually go through and try to prove it, you run into a difficulty. Certainly, it's the case that for any bisector, you know that the two angles formed must have a measure half that of the original by the angle addition axiom. But if you construct this angle, it's not actually obvious that it lies in the interior of the angle that you started with. One can prove it, but it's not straightforward. So that's actually not the best approach to use there, surprisingly. A better way of going about it is the following: is to use some of the tricks that are, or the theorems rather, that we have so far. So the first thing to note is, let's stay consistent. Let's do BAC. First thing to note is that, of course, we can choose any point on the ray AB as our point B. This point doesn't matter. We can move it back and forth along the ray. And in particular, we can go ahead and choose B and C along these rays such that they have equal distance from A, so that the segments AB and the segment AC are congruent to one another. This is not, this isn't asking much. And now we can construct the segment that lies between A and C. Now, intuitively, the angle bisector should probably go through the midpoint of that segment. So let's go the other way. We know that we can construct this segment in such, we can construct this segment BC and choose D to be the midpoint of it. We know every segment has a midpoint. And now we can try constructing the ray AD. So what's helpful here in this construction is that D is in the interior of angle BAC, since D is in the interior of the segment BC. We had that theorem way back when we were first talking about interiors, that in a triangle, every point on the side of a triangle, except for the endpoints, is contained in the interior of its opposite angle. So we know that D is contained in the interior of angle BAC. So that satisfies the difficult part of the definition from the first way of doing things. The next step is to try to show that the angles BAD and DAC are congruent to one another. But here's where we can use our theorems. By construction, we know that AB is congruent to AC, and that BD is congruent to CD. Those are both by construction. We chose our points in such a way to make that happen. And of course, because congruence is reflexive, we have that AD is congruent to AD. What that means is that the two little triangles that we have inside our diagram here are congruent. That means that triangle ABD is congruent to triangle ACD by side, side, side. From there, we have that corresponding angles are congruent, and therefore that'll tell us that the two angles we want are congruent, and that gives us the existence of the bisector. The uniqueness of the bisector will follow a similar path. If you assume you have a bisector, then by the crossbar theorem, it has to intersect the segment BC, and you can show, using our congruence theorems, that it has to intersect at a midpoint, but we've already shown that every segment has only one midpoint. And that's the idea behind how we prove that every angle has exactly one bisector. All right, so angle bisectors are ones that we'll use occasionally. Let's now talk about perpendicular lines. There's nothing real surprising about this definition here. Definition 53, two lines that intersect and whose union contains a right angle are called perpendicular. There's nothing clever, there's nothing unusual, about this. We call two lines perpendicular. They have to intersect, but if they contain at least one right angle, then we say that they are perpendicular. Now, we've already shown, in fact, that if a union of lines contains a right angle, it actually contains four right angles. So it would be equivalent here to say that that two lines are perpendicular if and only if they contain four separate right angles. But it's enough just to require that they have one. So that's what we're going to describe as perpendicular lines. And then we have an existence and uniqueness theorem for perpendicular lines as well, which again uses congruence of triangles. So theorem 54. Given a line L, point P, and plane E containing L and P, there is a unique line L prime such that P is in L prime and L prime is perpendicular to L. Oh, I forgot to note in the definition above the notation. We write L is perpendicular to L if L and L prime are perpendicular. So we've got this theorem here that says that if I take any line and I take a point And the point might be on the line, it might not be on the line. But if I take a line and a point and some plane containing all of those, then there has to be some line that goes through this point that is perpendicular to L. This winds up being quite important to us. Now, this takes a little bit of work, so let's take a look at that. So we're going to separate this into two cases. We're going to consider first the case that P belongs to L, that P actually lies on the line, and next the case when P doesn't lie on L. So so consider first the case P belongs to L. Let H be a half plane of E with L as an edge. Now, let's let Q be an element of L other than P. So we know that there exists a ray PR with R in the half plane H such that the measure of angle QPR equals 90 by the angle construction axiom. Therefore, that tells us that angle QPR is a right angle. So that means that the line PR is perpendicular to the line L. Also, by angle construction, this line is unique, because the angle construction axiom says that there is a unique line, or a unique ray rather, that goes through, that forms an angle of measure 90. And we know that all right angles have measure 90. So angle construction gives us the situation here. So that's the case when P belongs to the line L, and that's the easier case. So now let's consider the more complicated case. So now suppose that P does not lie on L, and let's get ourselves a diagram for the situation here. At a point P, and we would like to construct a line that goes through P and L and is perpendicular to L. Now we're going to do something very similar to what we did with side, side, side. All we know, we don't know a whole lot about L. It's just some random line. But one thing that we do know by axiom I5 is that it contains at least 2 points. So let's let Q and R be 2 points. On L. So they might look like Q and they might look like R. Actually, let me call them A and B in order to stay consistent with my notes. So now, what I want to do is I want to construct another point on the opposite side of the line from P that's sort of symmetric around it. Somehow get this sort of symmetry so that, you know, this line down here should hopefully be the perpendicular one. So let me call that point P prime. Let's make this precise. So by the angle segment construction theorem, there is a point P prime on the opposite side of L from P such that the angle BAP is congruent to the angle BAP prime, and the segment AP is congruent to the segment AP prime. So we're going to construct things this way. All right, so now we want to let G be an L such that P, G, P prime, so that G lies between P and P prime. We know that such a thing exists because P and P prime are on opposite sides of L. All right, so let's go from here. We definitely want to claim that the line containing P and P prime is the line that we care about. So let's give it a name. Let's let L equal the line P prime. Here again, we have to consider a couple of cases. So we consider two cases. Case one, let's suppose that G is actually equal to A. In that case, we have the following sort of setup. We've got P here, we've got the line L, P prime, A, and B. So in this case, we have that the angle BAP is congruent to the angle BAP prime, and we have that A lies between P and P prime because G is actually equal to A. So that means that the angle BAP and the angle BAP prime form a linear pair. But two congruent angles that form a linear pair are precisely right angles. So therefore, the angle BAP is a right angle. So that means that L is perpendicular to L prime. So that handles that fairly quickly. So let's look at case two. Let's suppose that G is not equal to A. Here we're again going to consider a couple of, technically a couple different cases, but we're not going to explicitly write it down this way. If G is in the ray AB, so that would be the situation like this. if G is in the ray AB, then the angle GAP is congruent to, or rather is equal to the angle BAP, because G and B lie on the same ray, which is congruent to the angle BAP prime, that's by construction, which again equals the angle GAP prime. And so that means pardon me, GAP prime. Yes, sorry. That's the end of that. I want to stop there. And then if G is not in the ray AB, then we have that A lies between G and B. We've got this sort of a situation. A, B, P prime. So that means that the angle GAP and angle GAP prime form a linear pair or form linear pairs, I should say, with the angle BAP and angle BAP prime, respectively. So we're looking at the angle GAP prime, and they're both forming linear pairs with BAP and BAP prime, respectively. Now, since the angle BAP is congruent to the angle BAP prime, we have that the angle GAP is congruent to the angle GAP prime. And I believe we had a result like this in the homework. The basic idea is that if two angles form a linear pair, then the sum of their angles is 180. And therefore, because the two blue angles have the same measure, and each of the green angles has to be the difference of 180 and the measure of the blue angles, the green angles have to have the same measure. So that means that in either case, whether G lies in the ray AB or not, we always have that the angle GAP is congruent to the angle GAP prime. So in any case, that means that the triangle GAP is congruent to the triangle GAP prime by side angle side. Therefore, the angle AGP is congruent to the angle AGP prime, so they are right angles, because they form a linear pair. So that would be this angle and this angle. Which finishes the proof, because then that shows that the line PP prime is perpendicular, to the line L, and that at least gives the uniqueness of it, or sorry, gives the existence of it. And then uniqueness. Oh, sorry. Let me go back previously. So uniqueness for this for the second case here is going to have to wait until the next section when we talk about geometric inequalities, and we're going to have a theorem that will show us that there can't be two separate perpendicular lines from a point to another line. All right, so that's our first introduction to perpendicular lines and some of the arguments that we have to use when working with them.